Hello friends, welcome to the online training program on tunnels and tunneling. This is the first lecture of this program on Introduction to Tunnels. I am Dr. Gopal Dhawan, founder and chairman of DDAG Private Limited. I will give you a brief account on status of tunneling in India. Then we will discuss developments in tunneling technology through ages, classification of tunnels, tunneling methodology, typical geological problems faced in tunnels, and finally, I will touch upon challenges we are facing while constructing tunnels in present times. Status of tunneling in India. We have several hydropower tunnels under construction, railway tunnels, highway tunnels, metro rail tunnels are also picking up, and lot of tunneling activity is going on for construction of metro rails in big cities of India. Then we have small diameter sewage tunnels and water storage tunnels. Railway sector was first to develop tunnels. Maximum tunnels were constructed for hydropower projects. Now, long and larger diameter tunnels are being constructed for railway and highway both. Rough estimate, total length of tunnels already constructed in India is about 2,700 kilometers, out of which 500 kilometers is in hydro sector alone. Total length of under construction tunnels is estimated to be about 700 kilometers, whereas the planned and proposed tunnels measure about 600 kilometers. Sector-wise distribution of planned and under construction tunneling projects in India is as follows: hydro 39%, irrigation, water supply and sewage 21%, rail tunnels 18%, metro tunnels 11%, road and highways 11%. In recent times, construction of many long tunnels have been taken up in the Himalayas. From the above data, you will see that hydro and irrigation sectors are dominating the scene, but as far as speed is concerned, it is much better in railway, metro and highway sectors. The speed of construction is much faster for rail, highway and metro tunnels. Tunneling technology through ages. There has been a remarkable progress in the technology during the last 100 years, but let us understand how it has progressed gradually since it first started in ancient times. Tunnels were hand dug by several ancient civilizations in the Indian and Mediterranean regions. Cut and cover was used in Babylon about 4,000 years ago. The technique is still employed today. They developed irrigation tunnels to carry water from river Euphrates. Sometimes fire was used to heat a rock obstruction by dousing it with water to crack it apart. Gunpowder was used to blast a 160-meter long canal tunnel in France in 1681. Next two major advances came around the year 1850 when nitrogen glycerine stabilized in form of dynamite replaced the less powerful black powder in the tunnel blasting. The second development was steam and compressed air was used to power drills to create holes for explosive charges. In the same period of time between 1820 and 1865, British engineers Mark Brunel and James Greathead used tunneling shield for two tunnels under Thames River. The first drilling jumbos were devised to dig diversion tunnels at Hoover Dam. These jumbos consisted of 24 to 30 pneumatic drills mounted on a frame welded to the bed of a truck. This innovation resulted in progress in tunneling at a record-breaking pace. Nowadays, modern jumbos allow a single operator or through artificial intelligence to control several drills mounted on hydraulically controlled arms. Of shield tunneling, which was initially started by Mark Brunel and James Greathead in 19th century, got extended to development of tunnel boring machines and thereby evolving the modern day double shield TBMs of various hues. In 1954, while building diversion tunnels for construction of a dam in South Dakota, James Robbins invented the tunnel boring machine, the TBM. The modern TBMs are customized for each project by matching the type and arrangement of the cutting heads to the site geology. Developments in the field of supporting the excavated soil and rock mass. Since the soft soil is prone to collapse and it can clog digging equipment, freezing of interstitial water was used in the year 1900 in United States. Shotcrete was invented in the year 1907. However, its use as structural element was recognized only in 1960s when NATM, the new Austrian tunneling method, was evolved. Rock bolts have been around since 1940s. The pre-grouting was developed in 1970s and is in use ever since. The Norwegian method of tunneling, NMT, was introduced in 1980s and is being progressively developed as a prominent philosophy of tunneling, especially where hard rocks are found. Classification of tunnels. A tunnel is an underground route or passage driven through the ground without disturbing the overlying ground. These are usually classified based on their use. Railway, highway, and metro tunnels are grouped into traffic tunnel or transportation tunnels. Then we construct hydropower tunnels for conveying water under gravity or under pressure. Sewage tunnels, water pipes, cable tunnels, and underground parkings are clubbed as public utility tunnels. Tunnels can also be classified based on the tunneling media through which it is excavated. Based on this, we can group tunnels into three categories: tunnels in hard rock, tunnels in soft materials, and tunnels in water-bearing soils. Some examples of important traffic tunnels or highway tunnels. The first is the Atal Tunnel or Rohtang Tunnel, which has been commissioned recently. Its construction began in the year 2008 and the tunnel was inaugurated by our Honorable Prime Minister, Mr. Narendra Modi, in the year 2020. It is built under Rohtang Pass in the eastern Pir Panjal range of Himalayas. It measures about 9 kilometers long. It is the longest single tube highway tunnel above the elevation 3000 meters in the world. It has faced several challenges during its construction. Some of the important ones are harsh climatic conditions, occurrence of avalanches, flowing ground conditions in the tunnel in a fault zone or high cover areas. Example is from Norway. Here the Lærdal tunnel, which is 24.5 km long, this connects Lærdal and Årland on the highway between Oslo and Bergen. It was built to avoid road crossings in winter. It is mainly constructed through Precambrian gneisses, which was mostly solid, but rocks were cracked and broken in few zones. There were frequent rock bursts requiring special safety initiatives in the high cover areas during construction of this tunnel. Examples are from Switzerland. Here 3 tunnels have been constructed under the St. Gotthard Pass during the last century. The first tunnel is a highway tunnel which is marked as a crescent shaped tunnel with right dots on this map. This is a 16.5 km long tunnel. It was constructed in 1980s. It was the longest road tunnel in the world at the time of its construction, and now it is the 5th longest. You can see the south entrance of this tunnel in this picture. Then the rest 2 tunnels were constructed for railways. One is marked with the black dots on the map. This is Gotthard railway tunnel, and the other one is Gotthard base tunnel. Gotthard base tunnel is about 57 kilometers long. 1 kilometer long Gotthard base tunnel is world's longest railway and deepest traffic tunnel today. The third tunnel is Gotthard tunnel, which was marked as black dots on the map. This was the first tunnel which was built to pass through St. Gotthard Massif. Its length is 15 km long. Its construction took place in 10 years. When it was opened in 1882, it was world's longest tunnel. The boring process involved the first large-scale use of dynamite, which was relatively recent innovation at that time. Several railway tunnels are under construction in high mountain ranges of Himalayas. First one is Rishikesh-Karnaprayag railway line. It is located in Uttarakhand state of India. The project is about 125 km long railway line being constructed by RVNL, the Rail Vikas Nigam Limited. This route includes construction of 35 bridges and 17 tunnels. A 15 km long tunnel between Devprayag and Lachmoli is one of the longest planned rail tunnel in the country in this project. Nagar-Baramulla rail link project is another important railway project under construction in Himalayas. Total length of this railway line is 272 kilometers long, out of which 161 kilometers has already been commissioned. You can see it on the map that section between Udhampur and Katra has been commissioned. Katra to Banihal section is under construction, and Banihal to Baramulla is commissioned. This project involves in total about 114 kilometers long tunneling in the entire route. The T49 tunnel, which is located between Sumbhar and Arpinchala stations in the Katra Banihal section, is the longest tunnel. It is the longest Indian Rail Tunnel as of now. It was successfully completed in February 2022. Metro railway projects. Kolkata East-West Metro line. This is being constructed by Kolkata Metro Rail Corporation Limited for connecting Howrah and Kolkata. Here a 520-meter long twin tunnel is being constructed. This is a crucial link for 16.6 kilometer long East-West Metro line project. This is an underwater tunnel. Here a station is also being built under Hooghly River at a depth of 33 meters. Another example of underwater tunnel is from Mumbai Metro Line 3, where a 170-meter long twin tunnels passing under the Methi River will be constructed between Barla Kurla complex and Dharavi stations. Construction of any hydropower project involves construction of several types of underground structures. For example, intake tunnels, headrace tunnels or HRTs, desilting chambers, pressure shafts, adits, main access tunnel to underground powerhouse and tail race tunnel. Water from reservoir is drawn through an intake tunnel or intake structure. Then it travels through HRT, headrace tunnel, connects headrace tunnel with the surge shaft, and then this vertical portion is known as pressure shaft tunnel. It goes to powerhouse for power generation, and from powerhouse, after power is generated, it goes through the tail race tunnel and connects the river again. Construction of tunnels require two major operations. One is the tunnel excavation and the other is tunneling support after the tunnel is excavated. Excavation can be done either by drill and blast method or by mechanized tunneling. In drill and blast, which is shown in green color, we may have full face if the rock is good, or if the rock is not good or the tunnel is being constructed through soft sediments or riverborne material or any kind of overburden, we will have to resort to partial face excavation, which is also known as multiple drifting method. Under the mechanized tunneling, we may have shield tunneling, road headers, alpine miners or TBMs. TBMs are also divided into several types. There are two types of TBMs. Mainly, TBMs are classified into two types. The first is hard rock TBMs, which may be a gripper TBM or a shielded TBM. A shielded TBM can be of single shield or double shield. Then under the soft rock TBMs, we may have earth pressure balanced TBMs, EPB TBM. Then next type of soft rock TBMs is compressed air TBMs, and lastly the slurry shield TBM. Tunneling support methods or philosophies involve several types of supporting elements, but how these support elements are to be installed during construction of a tunnel depends upon the type of tunneling support philosophy you are adopting. It could be the conventional tunneling philosophy, You may choose the ground support interaction method, observational methods of tunneling, the new Austrian tunneling method, which is also known as NATM, or Norwegian method of tunneling, which is known as NMT, or Edico-RS method of tunneling. We will learn in detail about each method of tunnel support philosophies in the forthcoming lectures. And typical geological problems which we have faced in tunnels during construction of tunnels. First group of problems can be grouped as cavity formation, chimney formation, flowing ground conditions in tunnels, high ingress of water in tunnel or TBM submergence, daylighting of tunnels in low cover zones if quality of investigation is not good or inadequate. These type of problems could be faced. High stress related issues, that is rock busting, spalling or squeezing. This is normally experienced in tunnels which are driven through high overburden cover. High temperature conditions have also been faced in two tunnels, namely Sanjay Gandhi Tunnel in Himachal Pradesh and Dhauliganga Tunnel, which was a hydropower station in Uttarakhand. Emission of noxious gases. There was a deadly explosion of methane gas in Loktak Tunnel in early 70s. Due to this explosion, about 100 people died. Then the last group of problems is due to variation in the predicted rock mass classes and the actually encountered rock mass classes. We will discuss this in detail in our subsequent lectures. Here are some glimpses of geological problems faced during construction of underground structures in Himalayas. The first photo is muck flow from shear zone during TBM excavation at Dulhasti project in Jammu and Kashmir. Second photo is silt accumulation at the TBM phase at Parvati 2 project. The third photo is also from Parvati 2 project where high ingress of silt mixed water was faced. In the second row, we have squeezing ground condition in headless tunnel of Teesta 5 project, and second photo of second row is rock busting at Parvati 2 project. The last photo is from Dhauliganga headless tunnel where high temperature conditions were faced. And what is the root cause of all these problems? Most of the tunneling projects being constructed in Himalayas encountered frequently varying and sometimes unknown geology leading to stability problems. The second group of problems is related to high overburden cover. When the tunnel passes through high overburden, there could be following problems. If the overburden is high, then the high in situ stresses will be experienced. And if the tunnel media is soft ground, then squeezing will take place in such situation. If tunnel is being excavated to hard rock mass, then rock busting will take place. And if we encounter aquifers or water bearing strata, then flooding or high ingress of slush will take place. The third group of problems occur when the orientation of discontinuities is unfavorable, and if the same is not supported in time, then there could be wedge failures, and this could lead to cavity failures or chimney formations. What are the challenges the tunneling industry is facing today? There are issues related to geological models. During the design phase, and the tender stage, it is difficult to have a dependable geological model due to inadequacies in investigations. For the same reason, it is difficult to locate major shear zones or water-bearing zones. There are a lot of problems which are encountered due to variations in rock classes, and this happens because of projections from distance. Minimizing uncertainties is one of the major challenges before our industry today, and selection of tunneling methodologies is also to be done very carefully in the light of investigation data, or we have to improve our investigation data so that right kind of tunneling methodology can be selected at the tender stage or design stage. What are the constraints which are holding us in spite of our best efforts? There is remoteness of projects in mountainous regions. There are issues related to accessibility or inaccessibility. Outcrops in Himalayan region are very limited, so we have to depend upon projections from distances. There are limitations of exploratory techniques. There are issues related to uncertain occurrences of groundwater and heterogeneity in the tunneling medium, and urban tunneling has a different set of problems which we will discuss in subsequent lectures. So how to proceed further? What is the way forward? In my opinion, synergy between the geologist and engineer is a must. The geologist and engineers working at site must be trained and aware of the latest developments in their respective fields. A geologist must provide the information to the designer or engineer to the best of his capabilities. Designers and engineers must understand limitations of the geologist and should be ready to tackle problems due to unknown situations. Together, we should come up with the best solutions for the project. Of references, I have also suggested some material or papers for further study with my lecture notes. Thank you for your attention, please.